So in lecture 1 for chapter 20, adaptive immunity, we look at cell-mediated immunity. Now we're going to look at antibody-mediated immunity or humoral immunity. Humoral immunity. And our second lecture for adaptive immunity in chapter 20. So antibodies are made by our B cells. They are proteins secreted by the B cells. And they are also known as immunoglobulins or gamma globulins. So just like with our T cells, B cells are going to recognize a specific antigen, and it will trigger it to change and secrete antibodies to the owner of that antigen. These immunoglobulins have several mechanisms that they will use to lead to the destruction of the pathogen that antigen was derived from. And then our third phase here is that just like with our T cells, we develop memory so that the next time that antigen is encountered, it will be a much quicker, swifter, stronger reaction to the pathogen. So of the B cells that are generated in the bone marrow, only about 10% of the cells finish their maturation. And that's because we have that self-selection again. And so any cells that are self-reactive are destroyed. This helped to prevent autoimmunity and any autoantibodies being made. Autoimmune disorders are a difficult disease and not something you really want to deal with. So B cells encounter the antigen, binds to the receptors on the B cell. Once it binds to the receptors on the B cell synthesizes, processes the antigen, and presents it on a class 2 MHC. Because remember, class 2 presents exogenous molecules, and these antigens were picked up outside the cell. Once it puts it on MHC2, that is a T helper cell receptor, and so it binds to a T helper cell, which then secretes cytokines that will activate the B cell to start dividing. Once the B cell starts dividing, we will have plasma cells, which are the cells that secrete antibody, but we will also form a few memory cells so that if we see this antigen again, we can elicit an even stronger response. Let's look at this video of activation of B cells.
Activation of naive B cells occurs in lymphoid tissues and organs such as the lymph nodes. It begins with clonal selection when an antigen, such as a virus, is recognized and binds to a B cell receptor. B cell receptors are actually antibodies on the surface of B cells. A B cell bound to an antigen is considered sensitized. The sensitized B cell then internalizes or ingests the B cell receptor antigen complex by phagocytosis. After processing it, the B cell displays the antigenic fragment on a class 2 MHC molecule on its surface. As we learned earlier, helper T cells can recognize antigens bound to class 2 MHC molecules via their T cell receptors. When an effector helper T cell recognizes the class 2 MHC antigen complex presented by the sensitized B cell, it secretes cytokines that cause the B cell to become fully activated. Once activated, the B cell undergoes proliferation by dividing repeatedly. The majority of the newly produced B cells differentiate into plasma cells. These plasma cells secrete antibodies specific for this particular virus. The antibodies then travel to the site of infection via the blood. There they bind and neutralize the viral particles so they cannot infect cells. Finally, some of the B cell clones become memory cells. These cells can quickly respond to future infection by the same virus.
So we have 5 classes of antibodies: IgG, IgA, IgM, IgE, IgD. IgG, IgE, IgD are monomers. IgA is a dimer. IgM is a pentamer. IgG makes up the most of our antibodies. Only antibody that can cross the placenta from the mother to the fetus functions in opsonization, neutralization, complement fixation. IgA is in secretion, so mother's milk, tears, saliva. It is what gives an infant its immunity for the first couple of days or first several weeks of life. Functions in agglutination and neutralization. IgM, first antibody expressed with our primary exposure, potent agglutination and precipitating, and functions with complement fixation. IgE plays a role in our inflammatory response, binding to mast and basophils, eliciting the release of those inflammatory mediators, in particular an allergic response. And then IgD, that is that antibody that we saw expressed on B cells that allows them to become sensitized. Here you can see the visual depiction of what happens. Agglutination is when the antibodies bind to a large bacterium, cell, something that is not soluble in a liquid, and causes it to agglutinate, clump together. Whereas a precipitation is an antigen that is dissolved in the liquid it is in, and the antibody, in this case looks like IgM with the pentamer, causes it to precipitate out of solution. We can have opsonization, just like we saw back with the complement, where antibody coats the bacterium, cancer cell, whatever is needing to be phagocytized, enhance that phagocytosis. Same as with complement, antibodies can neutralize things such as viruses, but it can also neutralize toxins, snake venom, spider venoms, toxic substances that get into our system. Antibodies react with complement, lead to cell lysis with our membrane attack complex, and so they help to enhance complement activation. And then stimulation of inflammation, we just saw with IgE, is going to bind to and stimulate mast cells or basophils to release those inflammatory mediators. With our primary and secondary immune responses, when we are first exposed, mainly make IgM, takes us about 7 to 14 days to reach our antibody peak, and is predominantly IgM followed by IgE, duration of about 14 to 21 days. Has a lag time of about 4 to 5 days before you get any antibody production. But now on our second exposure that we have memory, so we develop memory, lag phase is only 1 to 3 days. Time until antibody peak is 3 to 5 days. Primary antibody is our IgG. And then 28 days and beyond. So we can have long-term antibody levels that help us to combat whatever stimulated that response. With our antibody-mediated immunity, we can have natural. Natural means that we make it. We develop memory. And that means next time we see it, we'll get even a better response. So we can give naturally acquired through exposure in nature. So you come in contact with somebody with the flu and get the flu before you ever get vaccinated. Artificial would be getting vaccinated to build up some memory so that you can respond more quickly when you encounter it naturally. Passive immunity, this is what we were talking about with those IgAs, where they can be passed from mother to child. They are passed through the breast milk. So naturally acquired, but short-lived because you're not making it yourself. You can also get it artificially. So if you get bit by a snake, they tend to give you antivenom. Antivenom is antibodies against the toxin in the venom so that it can prevent you from dying from the snake bite or the brown recluse bite or whatever toxin you've been exposed to. But again, no memory is formed, no lasting protection, and the antibodies are made by somebody other than you. All right, so let's look at our big picture animations. So with the common cold, we first get this innate response. with inflammatory mediators, natural killer cells, interferons targeting the other cells and recruiting the natural killer cells. Once we start this innate response, then the adaptive immunity will kick in. That virus binds to the IgD on the B cells, sensitizes them, stimulates them to make plasma cells. The antibody also, the dead cells from the cytotoxic response will be phagocytized. And so those dead cells are phagocytized, presented, activate both our naive T helper cell, which will release cytokines, enhancing the B cell activation and enhancing cytotoxic T cells, which will come and destroy any virally infected cells directly because it's presented on that MHC1 complex because it's an endogenous antigen. Antibodies will neutralize the viral particles that are floating around in your system. With a bacterial infection, again, innate immune system is the first. Macrophages first to the line. Remember, this is part 2 of our inflammatory response. We've got the leaky capillaries with all the signs of inflammation, redness, heating, swelling. Then we recruit through chemotaxis our neutrophils. They cling to the capillary walls with margination, diapedesis to come out. And then they start also phagocytizing any of the bacteria that are around. Release more chemotaxic, recruit more of those antigen-presenting cells. The macrophages are going to present to the T helper cell. The T helper cell will activate, release cytokines to enhance phagocytosis even more, release cytokines to cause the plasma cells to make even more antibodies. The bacteria bind to naive B cells, sensitize them, and send them into clonal selection to make more antibodies, which will then agglutinate the bacterial cells and make them ineffective. Target them also for phagocytosis. Here's that whole picture with the innate and adaptive immune responses. Cancer. Cancer is a mutation from within, so it is endogenous. Natural killer cells usually are the first to the scene, the innate, releasing interferons, targeting the cells to be destroyed by our dendritic cells and our natural killer cells, presented by the dendritic cells to the T helper cells, which release cytokines, remember interleukin 2 in particular, to activate our cytotoxic T cells, which will then come and destroy the cancer cells, presenting the mutated DNA that caused them to become cancerous on those MHC1 complexes. And the cytotoxic T cells put in the perforins and lyse the cells, degrading the cancer cells themselves. And here you can see it a little closer up. Disorders of our immune system, hypersensitivities, immunodeficiencies. Overreaction of the immune system is hypersensitivity, immunodeficiencies when it fails, and the autoimmune is when it attacks self. And so with our hypersensitivity going to be IgE and our mast cells or basophils releasing those inflammatory mediators, in particular histamine. That's our type 1. Type 2 will be antibody mediated. This is when you get a mismatched blood type. Or penicillin will cause erythropoiesis or the complement erythrolysis. Lysis causing the red blood cells to lyse. Type 3, immune complex mediated hypersensitivity with soluble antigens. Get deposited all over the body, kidney, blood walls, synovial fluid, causing severe inflammatory responses in those areas. And then once deposited, that inflammatory response will attract the neutrophils, which can damage the affected tissues with the soluble antigens deposited. And delayed type hypersensitivity. This is usually a T cell versus an antibody response. Activating recruiting macrophages, sometimes cytotoxic T cells. Usually takes 2 to 3 days. and multiple exposures to have a severe reaction. Some examples of delayed type hypersensitivities are when you react to poison ivy or poison oak, a contact dermatitis, or when you have a reaction to the microbacterium tuberculosis because it is contained within the cells and an intercellular pathogen will cause a delayed type hypersensitivity. Immunodeficiencies. So you can be born with it, have a genetic defect. This is a primary called severe combined immune deficiency, SCID. And then a secondary immunodeficiency is acquired. This is AIDS, acquired immunodeficiency, most notable from HIV, but you can also get it from trauma, cancer, or other medications. And then our autoimmune disorders. This is where we start attacking self. Multiple sclerosis is an autoimmune disorder. It's where the body destroys the myelin sheath, and that's why it travels and moves around, because once it destroys the myelin, it moves to another area that has myelin. Then it destroys it, and then the myelin grows back, and then it moves somewhere else. You can also have where foreign antigens mimic self-antigen. This is rheumatic fever. So normal T cells don't normally attack, but they lack co-stimulatory signals. When you get rheumatoid fever, you get the co-stimulatory, activate T cells, and they may attack self. And then inappropriate expression of MHC class 2 molecules. This is the type 1 diabetes mellitus, where the pancreas expresses as an antigen-presenting cell, and on a class 2, which causes the destruction of the insulin-producing cells in the pancreas. And that leads to the type 1 diabetes mellitus. Pathogens with production of cytokines with non-specifically activate B cells resulting in autoantibodies. And lupus, erythematosus, with certain viral infections, leads to the production of antibodies and DNA, erythrocytes, platelets, leukocytes. And that's it, folks.